In section 4.8, we're going to be talking about analyzing graphs of polynomial functions. We'll be adding to our previous knowledge of n behaviors and what are the intervals over which we're increasing and decreasing as we move from left to right. To get a little bit more specific, things that we'll be learning about include x-intercepts. And our x-intercepts, remember, are going to be synonymous with our zeros, with our solutions. And we can write those as factors. If k is a 0, we can express that as a factor as x minus k. Or if we take a polynomial and factor it and get to something like x minus 3, it tells us that 3 is going to be one of our zeros, our solutions, our x-intercepts. We're also going to use the location principle, or more formally, we're going to allow technology to use the location principle to help identify where zeros might be located. We'll talk about that specifically in a moment. We'll also talk about turning points. If we're going to transition from the function increasing to decreasing, then at some point we have to hit a local maximum. And same thing if we are going down and then up. Well, where is that local minimum point? And finally, in this section, we'll talk about even and odd functions. Example 1 asks us to use x-intercepts to graph polynomial functions. So we're asked to graph the function f of x equals 1/8 x plus 1 squared times x minus 4. And because this is written in factored form, we can real quickly identify where the zeros are located. Remember, the zeros are closely associated with the factors. So excuse me. So x plus 1 is going to lead us to -1, 0, and x minus 4 to 4, 0. So we can plot those points on our graph. And without multiplying this all out into standard form, if we just take a lazy man's approach, that first set of parentheses would give us x squared. And when we multiply times that second set of parentheses, we would come up with x cubed. Distribute the 1/8, and our leading term would be a positive 1/8 x cubed. The positive for the leading coefficient is going to tell us that ultimately to the right our function is going to be increasing, and because the function is cubic, because that exponent is an odd value, ultimately to the left it's going to be going in a different direction, so in this case down. Therefore our n behaviors are going to be down up, and we can start to graph how that's going to look. Now, how do we get from 1, 0 to the next? If it's cubic, we should have that bend somewhere in between. And I notice that there's a double root located at -1, 0. If you look back up at the function, do you see that square? That's going to tell us that that's a double root, that's an even number, and at that point, we're going to bounce. So when we finish out this graph, we increase until we come to that turning point at -1, 0, and then we decrease. Ultimately, we come to some turning point, and then we start to increase. We go through 4, 0, and we increase forever. We could identify the y-intercept pretty quickly if we wanted to multiply 1 squared times -4, that's -4, distribute the 1/8, so -4 divided by, or times 1/8 would get us to -1/2. Now let's try to graph a second function where f of x equals -12 times x cubed times x plus 2 squared times x minus 3. Again, we're in factored form, so we can tell where our zeros are rather quickly. That x cubed leads us to the origin, x plus 2 leads us to -2, 0, and 3, 0 comes from x minus 3. So we can label those 3 zeros on our x-axis. And we can multiply out x plus 2 times itself, and we can multiply times x minus 3 and distribute the -1/12. But if we just are looking for the leading term, we can multiply -1/12 times x cubed times x squared times x. When we multiply the variables with different exponents, we add those together, and so we should wind up with -1/12 x to the 6th. And again, similar to the last time, we can look to see that our leading term is negative, and that means that ultimately as we go to the right, we'll be heading down. And our exponent is an even number, the 6, and so our end behaviors are the same. So if we go to graph those, we should have down, down, and we should look somewhat like what we have on the screen over to the right. Now, the last thing is, how do we get from zeros to zeros? Well, in the last example, we saw a multiplicity of 2, and when our exponents are even, we remember that we bounce. So that x plus 2 is squared, and so you can see on the graph, we come up until we get to -2, and then we bounce. And also, our graph continues through the x-axis if our exponents are odd. So the first one I would like to take a look at is that 1, x minus 3 raised to the first power. That 1 wasn't there originally, but it's considered to be there. And so if we put in the singular root, we pass directly through where x equals 3. The more difficult one is the x cubed. And when we have that, when we have a triple root, we are still going to go through at the origin. We're still going to go through at that 0, but we're going to soften out in between. So as we go from left to right, we are increasing until we get to that turning point, that 0 at -2, 0. We bounce, we come down for a little bit, and then we increase through the origin and continue to increase up beyond where I have us graphed. Ultimately, we hit a turning point, and then we come down straight through 3, and our end behavior tells us that we're going to continue down forever. So when graphing polynomials, they are smooth and continuous. Their domains go from negative to positive infinity. We've talked earlier about end behaviors. It stands to reason that if some function is coming from negative to positive infinity with regard to x, and at some point it's beneath and at another point it's above the x-axis, at some point it has to cross the x-axis. There needs to be at least one 0. The location principle would suggest that if you plug in some value of x and that's below the x-axis, plug in another and it gives us a value above, then somewhere in between those 2 points we should find a 0. So I have an example here where I've hidden the middle portion of this function. Between -2.5 and 3, I haven't shown what this function looks like, and yet I know that it needs to cross the x-axis somewhere. That last sentence over on the left tells us that there needs to be at least one real 0. We can find, in this case, there happens to be 3. Maybe we can factor and find those zeros. Maybe we'll rely on technology. But the point to be taken here is that if it's going to be continuous, passing from negative values for y to positive, there must be at least one 0. We can also use the location principle to help us find turning points. Once again, we have a polynomial graphed here, but in between the black points, the graph is erased. We're increasing from negative infinity all the way to -2.5. Something happens between there and the origin 0, 0, but you can see at 0, 0 moving to the right, for a while we're decreasing and then we increase again. Well, to go from increasing to decreasing, we must hit some turning point. We must hit a local maximum. Our graph looks something like this, and we'll be able to use technology to be able to locate those local maximum and minimum points. We call it either a relative maximum or a local maximum because you can see over to the right there's just one example of another point on the graph that happens to be higher than it. So that local maximum is not the highest point on the graph, but relative to that area of the graph, it's a local maximum. Similar to saying that our school, or Randolph in general, is at a high point in Morris County. But it's not to say that it's the highest point in New Jersey or the United States, but in our general vicinity, it's a local maximum. One of the final ideas in terms of graphing accurately is to figure out where are the turning points. We've gone from the extremes with end behaviors to the center where we're finding our x-intercepts, but in between x-intercepts, where are our local maximum and minimum values? Well, in this particular example, we have a cubic. We have something that is a degree 3, and so there is at most 2, which is 3 minus 1, 1 less than 3 turning points. So we see there's a local minimum and there's a local maximum point. We talk about the local maximum being that y value at that turning point, which is 0.77. The local minimum is going to have a value of negative 0.768. That's the y value of that turning point. In example 2, there's a graph drawn for us, and we're asked to identify the turning points. Can we talk about the local maximum and minima of the function? Minima is plural for the word minimum because you can see in black there are 2 minimum points. It's a quartic function. It's degree 4, and you can see that we are decreasing, increasing, decreasing, increasing. There are 4 different directions that we are heading in, and so there can be at most 3 turning points, and you can see those identified in black. The local maxima and minima are the y values of the turning points. So you can see the coordinates are shown there, but when we want to talk specifically about the local maximum, we're going to look at that turning point and say that it's 3.112. The local minimum point, that first one over on the bottom left there, is negative 4.237, and that second local minimum is at 0. Is at the 0.20, but the minimum value is 0. That middle point there, I have quotations around local because you can see that it is in fact the lowest point that that graph will ever get to. We don't necessarily know that as we're dealing with this, so we talk about it as being the local maximum. If it turns out that it is in fact the minimum value, so be it. And we use the terms like local and relative as minimum or maximum points to suggest that these extremes are only in relation to points around there. So is the turning point at the maximum the highest point that we will ever get to? No, the end behaviors are both pointing upward, so we can see that that function is going to increase towards positive infinity as we go towards negative and positive infinity for x. But locally, that turning point is a maximum. Finally, today we want to talk about even and odd functions. A function is an even function when f of negative x is the same as f of x, meaning that there's symmetry over the y-axis. If we focus simply on the even functions for a moment, you can see that there's a line of reflection along the y-axis. If we plug in value of f of x and out comes a y, if we plug in a value of negative x and out comes the same y, we have an even function. And we have an odd function when we plug in negative values for x if out comes the opposite of f of x. When this happens, we have rotational symmetry. That's symmetry about the origin of 180 degrees. That's to say, if we take our function and spin it a half of a turn around the origin, we will have an odd function. Finally, in example 3, we're going to evaluate functions to help determine whether or not they're even or odd. To do so, we're going to plug in a negative x wherever we see x and see what comes out. If the result is the same function as the original, then it's an even function. It means there's symmetry over the y-axis. If the result is that all of the signs are opposite, then it is an odd function. So on the far left, we begin with f of x equals negative x squared plus 16. Plugging in a negative x wherever we see x squared, with the order of operations, we first square negative x and that becomes positive. The negative on the outside leaves it as a negative x squared plus 16. That's exactly the same result as what we started with, and therefore f of negative x can be said to be the same as f of x. When that's the case, we have an even function. You can see points graphed below that correspond to this function, and if we fill those in, I hope you can see the symmetry over the y-axis. There's reflective symmetry. In our center column, we have x squared minus 4x minus 12, and again, wherever we see x, we're going to plug in a negative x. When we do so, the negative x squared comes out to being positive again, but the negative 4 times negative x becomes a positive 4x, and there's still the minus 12. So it looks very similar to the original, except that one sign is different. The difference means it's not the same, so it's not equivalent to f of x, but it's also not with all three signs being different, so it's not the opposite of f of x either. So f of x is not an even or an odd function. When we go to graph this, you can see the parabola below. You can see that there is symmetry along the axis of symmetry, but that symmetry is not over the y-axis, so it's not an even function. Something to highlight here is that although this is a parabola, although it's quadratic, although the exponent is 2, which is an even number, this is not an even function. Even functions are only that when they have symmetry over the y-axis. In our last example on the right, we have f of x equals x cubed minus 9x. Once again, wherever we see an x, we're going to plug in a negative x, and we are going to perform the order of operations. So we're going to take negative x and cube it. That will still become a negative, and a negative 9 times a negative x will become positive. So our result has what was a positive x cubed is now negative, what was a negative 9x is now positive. Both of those signs are different. That can be expressed as the opposite of f of x. When f of negative x is equal to the opposite of f of x, we call that an odd function. There are some points on the graph below. When we connect those, we'll come to find that there is rotational symmetry. That's to say that if we plug in f of negative x, what will come out is the opposite of f of x. I hope this tutorial has been helpful. Remember, we started with n behaviors and we started to then talk about x-intercepts. From x-intercepts, we also talked about turning points, which allowed us to decide how we were going to graph this with relative minimum and maximum values. And we also talked about even and odd functions with symmetry over the y-axis and with rotational symmetry about the origin. Your homework will be posted. Thank you and have a great day.